Hello everybody, this is Aslam. This question is from fall 2017, midterm 2, question 8. So first of all, take a minute, read the question, figure out what's going on, and work to an example if you can. It really helps clear things out. And then we're gonna walk it through together. Okay, so before we actually start the question, I wanna go over the subproblem types in DP really quickly, because I think that really helps deciding what to do with a DP question when you encounter one. So let's make this table first. Okay, so I have 4 things here. Okay, so first and the simplest kind of DP subproblems are when we have one variable and it is let's say 1 through n. And then our subproblem is, let's say, taking that variable from 1 to a certain value I. So in this case, the number of variables we have is usually linear. The second case is, again, we have one variable, but in this case, we don't have that set initial value. We're looking for different intervals for that variable. And in this case, our subproblem number, let me say number of subproblems is n squared. The third case is when we have 2 variables this time. Let's say we have x and y. Each of them, x goes to n, y goes to m. And our subproblem is basically the mirror of the first case. Each of them starts from 1 and then goes up to, let's say, I and j respectively. Oh, sorry, this is y. To y. Oh, no, what happened? Okay, I think the screen is fine now, yeah. So let's say y is going from 1 to j. And in this case, the number of subproblems is just going to be, again, relative to the size. And the last part and the last question is usually really hard to visualize and really hard to work with. The last case of DP problems is where the problem is basically a tree structure, and each subproblem is then a subtree of that original structure, and each subtree is ON, and the number of all subproblems is usually n squared. So what differentiates this last type of questions, the last type of problems, is that in the tree structure case, there's one really important property that you should probably know, that the result depends on the order that you do things. So order matters. So one really good example is the matrix multiplication from the book. How the order that you pick the matrices change your value. And in this case, what we usually try to do is either maximize the result that we have or make it optimized. And to do that, now we have this new thing to talk about, which is the order or the decision process that you do within the tree structured problem. Okay. So in this question, I put all A, B, C here, so we will have to move down. As always, we're gonna start by defining the subproblem. But first of all, let's visualize the balloons. So let's say we have a bunch of them, and we know that popping one of them is gonna create a noise. Popping one is gonna be the left one, and then the popped one. And then these are all sizes of the values, and the right. So we can clearly see that the order, the initial balloon that we're gonna select is gonna change basically the environment that remains after popping that. So this is basically the intuition that we should be able to say oh, the order that I pop the balloons is definitely gonna affect the maximum noise that we can possibly get. So an example would be let's say we have another balloon, and then let's call them balloons 1 to n. If I were to pop this balloon first, then the total number of, total noise that I would expect would be the noise that happened by me popping this balloon, and then this subtree, and the noise from this subtree. And each of these subtrees would be basically like all the balloons from, let's say, balloon 0 until one balloon before B, and then the remaining part would be like all the balloons after, let's say, until B1. So each of these cases, we can again like decide how to maximize the total noise coming from this or this. But essentially, by picking like one balloon, we are creating that subtree with that root B3 because we decide to pop that, and none of the next level subproblems is gonna contain B3 anymore. And that really shows that the ordering and the number, like the sequence of pops that we do, is gonna change the landscape of the question. Okay, so and another thing, this is kind of obvious, but these two subtrees are going to be kind of independent from each other. The one only like thing that the question already resolves is we will assume that like these are actually neighboring, like B2 and B4 in this case, after popping B3 is going to come together. But other than that, the maximum noise from this subtree is completely independent from this subtree because they contain different balloons. Okay. So, one other thing is, again, the question kind of mentions this, but in order to like understand it better, we have these dummy balloons on the sides that have the weight of like the size of 1, so that if we were to like, this is the original balloons, if we were to pop something at the edge, then our like right side for this balloon would be just 1. So we handle that edge case too. Okay, so far we basically said that our noise from popping one balloon is going to be the noise that is directly coming from it, and then the two subtrees that is going to result from that phase. Okay, so that makes, let's say, our subproblems in this case is going to be the maximum noise that we can get from a single subtree. So usually, like we already said this in the table here, like once we have a T structure, our subproblems are always going to be subtrees. And in this case, we defined a subtree as the balloons from like in this case we popped 3, but for the generality, let's say we popped balloon I, then that means our subtrees are going to be all the balloons from I to the N, which is the last balloon, and it is going to be all the balloons until I, which doesn't include I. So in this case, our subproblem is going to be the same thing as subtree, and we will define them as the maximum noise from popping balloons, that's way too many O's, balloons I through J. So again, like visually, I hope this kind of like resonates with you guys. This subtree is the same thing as whatever noise you can make using only these balloons, and that is going to be our subproblem. Okay, so after like writing your subproblem, there's always like, it is always good to like do that sanity check with like how the base case and the result that you want. So in this case, the result that we want is going to be the same thing as the subproblem that starts from the first balloon until the end. So yeah, we can represent our like bigger problem using the subproblem, which is nice, which is what's supposed to happen. Okay, so this was part A, I think. Yeah, so this is our subproblem. I hope this didn't take more than 3 lines. It shouldn't. And let's do the base case now. So base case, this was part A. Let's put part B here. So as we already know from like a bunch of classes, base case is the case that you can immediately answer the question. In this case, our question is like, oh, what is the maximum noise? So the only case that we can directly say what the maximum noise is if we only have one balloon to consider, right? Because if we have only one balloon, let's say this is the size S, we will automatically have like dummy balloons here. And the noise coming from this is just going to be equal to S, because multiplying both sides by 1 is doesn't change anything. Okay, so in our base case, we are dealing with only one balloon. And we know that we can represent this by like I to I. And this is going to be just the size. Okay, so let's look at the next question. Now we're going to write the recurrence relationship between our subproblems. Okay, so we already kind of talked about this in the visual part, saying that popping one balloon is going to be like the direct noise plus the noise from the subtrees. But let's like formalize it as the recurrence relationship. Okay. So we already said that the subproblem is basically handling all the balloons from I through J. Actually, let me move this down if I have space, and I don't have space. Okay, let me not move this down. We already said that this is basically the same thing as handling all the balloons from I through J, and we know that we want to maximize it. So the idea is, let me put maximize here, and then we're going to talk about what we are maximizing. But first of all, let's like think about this. If we were to like visualize the entire sequence of popping all the balloons, then what's going to happen is, let me do it here. So this is going to be the first balloon that you pop. So let's say BI, you pop this one. And then you will have different options. And each of the roots, as we already talked about, is going to be the balloon that you chose to pop within that subproblem. So like eventually, let's say like you have different things, and then you will eventually hit the leaves. And in this case, the leaves are basically going to be our base cases where we know what the noise produced from like popping that balloon. So the idea is, once we hit the base cases, we're in the territory that we can like talk about direct numbers, because for every single other like node, in order to talk about the noise creating from popping that, we have to know the subproblems, right? Because we don't know what happens after popping that. But in the last level, where we only have the leaves, then we know. So what we basically do is, at each level, our goal is to find the index. Let's say like after, even when we're choosing like the first balloon to pop, we want to pop the balloon in the index such that it is going to maximize the value. This is kind of given. But in order to do that, we have to start from the leaves and then go up again, knowing that we're going to like, this is going to be the last balloon we pop, which is really important to calculate the cost of the entire sequence. Okay, so let's start with like the known territory first. We know that this, so first of all, we said we want to maximize, and we want to maximize it over the indices of the balloons such that our subproblems are going to be starting from, oh my god, okay, is this better? Okay, starting from I until k minus 1, because as we talked about, our subproblems are going to be just everything that has to come before until the balloon that we popped, and then after the balloon till the end. So this is going to be one sub 2, and this is going to be another sub 3 after k. Plus, now we have to talk about the cost. So I really want to emphasize this. I emphasize the cost here because it is probably not what you expect. Also, this should be plus, obviously. So naively, we might think like, okay, like popping the kth indexed balloon is going to create the noise like the size of the previous balloon, that balloon, and the next balloon, right? This is like so clear, but it is not correct. And I really want to emphasize why it is not correct, because I think it is like such an easy mistake to do, and this is what like differentiates understanding like DP questions in like details like this. Okay, so we kind of already talked about like the leaves being the territory that we know and we have to move up. So the intuition here is that this cost should be the cost of creating and solving this entire subproblem. So once we solve this entire subproblem, this is basically saying we got rid of all the balloons through I to j. So like, let's say this is like the sequence of the balloons, and this is, oh my god, this is balloon I minus 1, this is balloon I, and then this is balloon like I, actually, let me do this differently instead of, okay. So let's say this is the sequence of the balloons, this is I, this is j, and we got rid of all the balloons here because that is how we defined our our subproblem. So the cost of handling everything in between this is then going to be defined by the last balloon you pop here times the noise coming from the new neighbors. So essentially, in order to like make this more clear, let's assume the last balloon that you have left between this interval. So it is going to be, so you will start by like I to j mini balloons, and then as you go through the subtree and as you pop like more balloons, the number of balloons are going to decrease, and eventually there's just going to be only one balloon here, and let's call it k. So this balloon, the noise coming from popping this balloon is going to be, of course, like the size of this balloon k times its neighbors, right? But now we already said that like if we're at the end of this subproblem, then we know that there are no balloons left. So then our new neighbors are going to be the two sides that are outside of our subproblem, which means on the left we're going to have I minus 1, the first balloon here, and then on the right we're going to have the first balloon outside of our subproblem, which is going to be j plus 1. So once we're at the end of our subproblem, the cost of solving this subproblem is going to be this value. And the important thing here is that this k is not the first balloon that you pop, but instead it is the last balloon, because the last level in your subtree is where you can deterministically talk about direct values and direct noises. So instead of like naively thinking, okay, let's assume I pop this one and then that one, we will just create the entire tree and talk about like the sequence of popping starting from the leaves up. And basically k is going to be the last balloon to be popped. And because it is the last balloon, the neighbors of k now are going to be s minus 1 and j plus 1 instead of k minus 1 and k plus 1, because we know that every other balloon within that interval is already popped and we already got our answer. I hope that makes it clear. This is a really cool question, so like make sure you understand why this isn't true and then this is true and amazing and smart and great. Okay, so we have one last problem, which is writing the pseudocode, but okay, let me find space to do this. Let's write the pseudocode in here. Okay, so the idea is, first of all, we already said this, but we need 2 dummy nodes, right, to make sure that we don't multiply things with wrong values. So let's say S0 and S0 is going to be 1, Sn plus 1 is going to be 1. These are our dummy nodes. And after that, we basically want to make sure that we have all the leaf values that we have. And what are the leaf values? They are the subproblems. Leaf is the same thing as looking at like a subproblem with itself, which is just going to be its own value. So for I in 1 to n, we want to make sure that I is going to be equal to its value that is before that, and after that we again multiply. This is just like reiterating what is given in the question. We set all the base cases, and then after that now we have to like iterate through the actual subtree. So one thing that you probably already know is, instead of like keeping track of like the initial value and the instead of like keeping track of I and j separately here, what we can also do is just keep track of the size of the subproblem and then iterate to the one variable and then keep the other one kind of constant. So let's do that. Let's say for size, our size is going to be 1 through n within that within the problem, and then let's just like use I for I, and I is also going to be iterating to 1 through n because we can start in any like index we want. And then if our s and I is determined, we know where our j is, because I is the initial value. That means j has to like end in I plus s. So for every single subproblem, okay, I don't have space here, but we just basically have to copy the, okay, let me write. This is so packed. I hope you can follow it. Okay, so we know that from the recurrence relationship, you should already know that we're trying to maximize the subproblem that is until k plus after k till j plus the noise coming from popping the last balloon in that entire subproblem, which is going to be last balloon. Again, I really want to iterate this, which is going to be the size of the last balloon and the previous balloons from like outside of the subproblems. And then do not forget to return the thing that we actually want to calculate, which was the biggest subproblem, which is the problem of the maximum value, maximum noise that you can get from the sequence that you choose to do. Okay, so this is basically it. I hope that makes sense. If it doesn't, make sure like you understand what's happening in this table. Make sure you can differentiate between questions, and make sure to differentiate between three structured questions. I think the easiest way to kind of see that is if like the order matters, and if the subtree, if like if your initial choice changes the landscape of the next sequences, then you have some sort of a clue that it is probably a T-structured DP question. And when you're writing the recurrence relationship, make sure that the cost that you're talking about is the cost of the entire subproblem rather than a specific balloon, because I think that's like the most common mistake, and it is really hard to understand if you don't have that intuition to talk about the cost of the subproblem rather than the cost of like a single decision within the subproblem, which is a huge difference. So I hope this was helpful. Go Bears! Yay!